Okay, now let us talk about finding Nash equilibria. We also will now look at more general properties of various games and their Nash equilibria, with the aim often to help find the people. By the way, whose pictures I have put here are, of course, John Nash on the left. He's famous in particular for suggesting the notion of stability, which is very famous, Nash equilibrium, and proving that a mixed game, a mixed extension of a finite game, all this possesses at least one Nash equilibrium. He also did things in cooperative games, in topology, and so on and so forth. But for us, his contribution is Nash equilibrium and its existence for mixed extensions of finite games. Now, the second person so the second from the left, John von Neumann, he was a great scientist in general. In our course, we see him at least in the notion of the idea of a game, zero-sum game, and the existence of an equilibrium there. So, also the von Neumann-Morgenstern, of course, utility here. But him you see all over the mathematics and theoretical computer science. So these are, of course, just two prominent figures, not the only important figures. So let us get to the work. We are going to talk about, again, finding Nash equilibrium, because it's the most famous solution concept for strategic form games, on which those form games we are now studying. Now, despite being very famous, actually about its existence and definitely about finding it, not much is known for general games. One thing which is actually known is that it's very hard for mixed games, mixed extensions of finite games, for which we know that it always exists. It also was proven about 20 years ago that it's very hard to find it in general. And also the pure equilibria, assuming that you know those exist, the finding a pure Nash equilibrium is also hard. So we actually know those things, but given a general game, just in this game, what are the equilibria? It's hard to find, and it's generally hard to characterize whether they exist. Actually, by the way, I want to mention that in the famous film A Beautiful Mind, which is generally great, the description of what they mean by Nash equilibrium is wrong, and in general, that's not something you should take as a reference for science or math. So it's a great film, of course, regardless. And since it's hard to say general things about equilibria, there is quite some research about subclasses of games where we can say something. So we are going to look at certain subclasses, but also general games. And we're also going to start studying about solution concepts other than Nash equilibrium, which is not often done in a basic course, but I think that at least on a basic level, it's important to study some, so that you have some general understanding of non-cooperative games. So the agenda of today is quite long. Actually, it's the agenda of all the lectures, so most of it will be given next time. And not so today we are going on to start this. It's the what is the domination, in the sense of what is a dominated strategy. We'll just recall that. We already studied that on the second lecture. Then we are going to study the notion of very weak domination and the notion of strict Nash equilibria. Those are minor variations on the notion of weak domination and Nash equilibria, respectively. And now the main thing is we have not recalled the notion of domination for nothing. We're going to study what happens if we delete some weakly dominant strategies. As we saw, it's not necessarily leaves the set of Nash equilibria intact. It can never add, but it does not leave them intact. But in the context of security and stability of a player, we're going to study what is the role of weakly dominated strategies, how important they are. Strictly dominated strategies are kind of not important, we say. But what is the importance of weakly dominated strategies? And we're going to finish this chapter on games, on strategic form games in general, by sketching the general algorithm for finding a Nash equilibrium and giving an example. Now we're going to look at some concrete subclasses of games, very broad subclasses, admittedly, but still concrete subclasses. First is going to be the constant time games, which we already saw. We're going to actually find an algorithm to again sketch an algorithm for finding its equilibria, because we can always apply the algorithm that I've mentioned. We're going to study for the general games, but we also can have a specific algorithm which uses those some properties of those games, some of which we're going to add today, in addition to what we've already seen. And then we're going to study symmetric game. That's also an important class of game, which, by the way, was also studied by Nash in his original paper, I think, on 51. Yeah, I think that's from the year. And then we're going to go to a general topic again after looking into concrete classes. And we're going to study another sort of concept, rationalizability. Now, that's a very natural solution concept, which talks about what we can know or what we assume players know. So it's a so-called epistemic game theory that will allow us to prove that when we delete strictly dominated strategies, the result does not depend on the order in which we delete those strategies. That's the result I mentioned, I think, when we mentioned that we have this notion of iterative deletion of strictly dominated strategies, but I didn't prove that. So rationalizability is an important solution concept which will allow us in particular to prove the order independence when we delete strictly dominated strategies. I remind you that deleting weakly dominated strategies, the result does depend on the order. Okay, so let's start with recalling the notion of domination. So given a game, strategy S is strictly dominated by a pure strategy, strictly dominated by a mixed strategy. If for any set of subprofile of what others do, S strictly works for the player I than this mixed strategy. Now strategy S is weakly dominated by the mixed strategy. If for every subprofile of what others do, S is not worse than P prime, and there exists at least one subprofile S prime minus I, the other such that the S is strictly. So given the definition of what it means that URS is strictly dominated by mixed P, because P does not have to be fully mixed, and you are. Now then we define the notion of S being just strictly dominated. That means that there exists something which strictly dominates that, and analogically is S is defined to be weakly dominant if there exists something, a mixed strategy, I mean, that weakly dominates F, such that S is weakly dominated by that. Okay, so now let us quickly remind those quite multiple properties we saw on the second lecture. Let us remind those. So, first, clearly, by definition, that being strongly dominant implies being weakly dominant. Now we also saw that a strictly dominant strategy is never in the support of a mixed equilibrium, because it's never a best response, and support equilibrium is always consists of best responses. Actually, it's characterized in that manner we saw. Now, a weakly dominated strategy can be in the support equilibrium, by the way. Now, a mixed Nash equilibrium is invariant to iterated deletion of finitely many strictly dominated strategies. So, when we iteratively delete finitely many strictly dominated strategies, the set of mixed Nash equilibria, in particular the set of pure Nash equilibria, does not change. It's important is it's finite many. Because now examples, it's usually going to be that way naturally, but we saw one example when we just can immediately delete infinitely many strictly dominated strategies, and then the set of equilibria of mixed Nash equilibria does change. So it's important to know that. As I said again, the process itself is often defined just deleting one by one, often is defined as something finite, so it's natural that we have this finite. In our case, we allow this to be infinite, but we just mentioned that if you want to have not to change the mixed Nash equilibria, you have to make sure that you delete finitely many strictly dominant. So it's not going to be hard to have it satisfy this property of finiteness. It's just that it's important to know that. Now, therefore, if we end up with a single strategy, then since that's going to be the only mixed Nash equilibrium, it means that the original mixed Nash equilibrium set, the original set of mixed Nash equilibria is also the singleton consistent of that strategy. Now, another property is that mixed Nash equilibria, the set of mixed Nash equilibria is not invariant to deleting weakly dominant strategies, even if you delete finitely many, it's not invariant, so it may change. But when you delete finitely many weakly dominated strategies, you don't introduce any new mixed Nash equilibrium. So if you end up with a single strategy, it's obviously even a pure Nash equilibrium, mixed and pure, you know that it cannot be a new one, so it did belong to the original set of pure Nash equilibrium. Now the deletion order matters when deleting weakly dominated strategies. We saw an example, and it does not matter when deleting strictly dominated strategies, as we will prove today. Not today in this set of lectures, on this slide. It will not do today. Now, talking about dominant strategies, let's go a bit further and introduce an important concept which is sometimes relevant. That you, in addition to defining a dominant, weakly dominant, we can it even further and define so-called very weakly dominant strategies. And you can guess what it is. Given a game, strategy S, pure strategy Si is very weakly dominated by a mixed strategy. If what the player gets for every set of sub profile of strategies for other players, what the player gets for his eyes, at most what the player gets for the very weakly dominated strategy. Now, unlike the case of a weakly dominated strategy, there is no need to ever have a strict limit. So a strategy in particular is always very weakly dominated by itself. Now, strategy is very weakly dominant if there exists a strategy. I think I need to mention here. It cannot be very weakly dominated by itself. It's important. It's important because if we allow that, it becomes meaningless, and we don't want it to be meaningless. So we want it to be meaningful. Okay. I want it to be meaningful, so let me change that. Okay. So I've changed the definition again. It's not something we are going to work with a lot. I just want you to have this notion. I've changed the definition in the following manner. So I'm not sure, by the way, that's the classical definition, but it does not matter. I just mentioned that it may be not the classical definition, unlike the other side. Strategy is very weakly dominated by another strategy if, first of all, it's always at least as good to use the other strategy than SI. Second, SI is not in the support of that other strategy. So Nova strategy can be dominated by itself. That's an important thing. And so we want to avoid this nothingness in the definition, or actually anythingness. So defining anything, because it will not be useful. Now, what's the use? The use is the following. So we first define before the strategy is very weakly dominated, if there exists something that such that S is very weakly dominated by the strategy. Now, it cannot be very weakly dominated by itself. It can be, on the other hand, very weakly dominated by a strategy which is exactly equivalent, gives exactly the same value. Player. Now, of course, weakly implies very weakly. And with the same proof holds the property that if you iteratively delete finitely many very weakly dominated strategies, it introduces no new mixed equilibrium. Now, remember that why doesn't introduce new mixed equilibrium? Because I said that, well, obviously you delete, you don't add any candidate, and you don't make someone who was not an equilibrium, because you don't introduce new previously non-existent deviations. Because for whatever you delete, you have someone who dominates. That's the logic. So that's why we need the dominating strategy to be independent of whoever you delete. Because if you allow a strategy to dominate itself, then maybe it's not actually so independent. And then you may not say that you delete that and you don't remove any deviation. So it's important that, despite that we don't require strict inequality, so we in particular allow for the same strategy. Basically, the only new thing is that strategy can be dominated by itself. It should not by itself. By the same strategy. That's important. Not by itself, by the same strategy. It cannot be itself. Okay. So I've given you yet another tool to, if you have just the same rows, you can just delete one of them. Or the same columns. That's the idea. But you have to eventually leave at least one. If you have 5 copies, you have to leave at least one. That's the idea. So that was the new thing. And then another sorting concept, simply in this vein of let's change the requirements. In this case, we are going to strengthen the stricter requirement in the signs. And we are going to say that a profile is a strict Nash equilibrium if for every player, it's not only that it's not worse, that it's never possible to strictly improve it, but strictly the best. For every player, for every subprofile of what others do, and for any deviation of the player, it's strictly better to keep what the player is doing than to deviate. For every player and strictly better. It's not enough that one player at least has a strict equality, but requirement game that every player has a strict magazine, and similarly, a strict mixed Nash equilibrium is a strict Nash equilibrium of the mixed extension. Now unless we say otherwise, we don't deal with non-strict equilibria. We just deal with equilibria, so we allow both kinds of inequalities here. But I want you to know this concept. And now let's talk about security, stability, and then what about deleting weakly dominated stuff. So the Nash equilibria in constant sum game are exactly the maximum property. So that's what we saw. Because it's important that in order for them to exist at all, we need to have this max min equal min max. Basically, the duality you can call it, because it can be seen through the proven through duality of LP. We didn't do that way, but it can be. Actually, the duality can be proven using that. So that's we know that it always exists if you have a mixed extension of finite game, because we know that it always exists a Nash equilibrium there. But in general, as long as we know that there exists an equilibrium, a Nash equilibrium in a constant sum game, they are exactly all those maximum properties. And also they are the secure property. So stability, equilibrium coincides with being secure in the sense that you're doing the best against the worst possible behavior of the opponent. Nice. However, for general games, security does not always coincide with stability. For example, look at the example from this Machler, Solar, and the Mir book. By the way, it's a great book. It's quite of a volume. I do recommend looking at it, but note please, they have quite a lot of other notation on what we have. So the unique Nash equilibrium is dangerous, as I said. Okay. So the unique Nash equilibrium is, you can check that it's bottom right. So it's equilibrium, but it's not secure. And how can you see that? What if player 2 chooses L and not R? When player 1 will suffer minus 100. That motivates our to choose the safer option, top. He will get not as good as 3, but almost. He will get 2 in all cases, regardless what player 2 does. Now, this reason motivates player 2 to choose the safest version L. Because if player 2 kept doing R and player 1 did top, player 2 would suffer minus 20. So then player 2 was motivated to choose L. Then that exacerbates one's fears that player 2 won't just, for whatever reason, won't play out. And that motivates player 1 to choose T even more, and the cycle closes. So it's actually quite reasonable for them, for the reasons I just said, to choose TL. It's not as good, but it's secure. It's more secure. Because then player 1 always gets 2, and player 2 always gets at least 0. But probably, in this case, 2. 1. Now, TL is also the only max min. So actually the general form for security is max min, right? Let's see. We do it here. So the minimum the role player can do for the column player is between 1, 0, and 2, 0. Between minus 21 and 3, minus 20. Now the meaning of the column player can, okay, let's just say that the best the column player, the max min the column player can do is of course 0. So the max min of the column player is 0, and the only is given when the column player chooses L. And as we already saw, we saw it in a concrete example, but now we see that it's basically the only max min strategy. Player 1. Now, what are the worst things player 2 can inflict on player 1? Now, that's when player 2 chooses T, it's 2. When player 2 chooses M, it's minus 10. And when player 2 chooses B, it's minus 100. And the max min is, of course, achieved by T, it's 2. So the max min is exactly TL. So that's exactly the safest version, or the only safe version actually in this case. But the only Nash equilibrium here is B bottom and right triple. Please pay attention that Nash equilibrium gets both players more than max min, and we'll actually see that it always gives at least max min. Now, so the most important point is that it's one of the from many examples that the stability equilibrium, let's say represented equilibrium, is not equivalent to safe to security represented by maximum. Now, the best pessimistic strategy is the one which achieves attains max min. And as I also say here, that in the infinite cases it may not exist if you have infinite strategies. Now, for mixed extension, it always exists because if that is a mixed extension of a compact, not even necessarily finite, in particular finite, but any compact set as I, and if the utility is continuous. Again, if Si is finite and any function is continuous with respect to the finite set, so in particular, it always exists of course in the finite case. Now, so we've seen that it's not the same security and stability, and let us now study that. So there may be several maximum strategies. Unlike what we saw before, that there is only one top left TL. There is another example also from Mahmoud and Zamir, where you have several maximum strategies. So here the means that player 1 can be picked up on player 2 are 1 and 1. So any strategy of player 2, any column is max min. What player 2 can inflict on player 1 is 0 and 1. So only bottom is max min player 1. So there are two options for max min, either bottom layer or bottom right. And for both players, of course, it's better to play bottom left, but they're both max min. Now, there is a very simple theorem from Mahmoud Zamir. And that's that the weakly dominant strategy is a best response for any strategy profile of the others and the maximum. Why? Well, let's S be weakly dominant strategy of player 1, a weakly dominant strategy of player 1. Now, why actually I even don't have to say A, because if there is a strategy which would dominate everyone, it's unique, because if you have two strategies, so you need to dominate one another, and it's impossible because there is this demand for strict equality at this one. So, not only strict domination, but also weak domination is unique. very weak is not, but we don't work with them. So let S be the only weakly dominant strategy of one. Now let us actually write that. It's important. Let S be there. It's unique. The weakly dominant strategy of one. It's unique. So let S be the weakly dominant strategy of one. It's a best response when you have strategy profile by definition of being weakly dominant. Now we just need to prove also the quite simple statement that it's a max-min, and for any strategies of the others and any S prime, S is at least as good as S prime. And that's also true if you minimize over the strategies of the others. And therefore, S is a strategy which attains a maximum. So S is a strategy, and it's a maximum strategy. Okay, please notice that we define this max-min and all that for any game, not only for constant sum game, not only for two-player game. It's important. There's something to mention. Because previously we spoke about only, we started speaking about max-min in the context of a two-player zero-sum game. Now another thing about security and stability that so that if a profile is a vector of weakly dominant, then it's a Nash equilibrium. Well, it's a vector of best responses that we saw. It's a Nash equilibrium, and it's a vector of max-min. So it's a vector of max-min. That's simply what we said, just for a vector. It's often what we actually would love to get in mechanism design. We would like to find a game. It's something we don't do here, but in mechanism design, people look for games where something which you like is an equilibrium. Now, if there is something which is weakly dominant, and it's also a vector of max-min, or excuse me, it's if it's weakly dominant, it's great. Why it's great? It's great. It's reasonable to expect it to happen, but in particular, it's both stable, in Nash equilibrium, and secure. So that's one of the reasons why it's so. Now, a weakly dominant thing is a Nash equilibrium and a vector of max-min. Now, but there may be other Nash equilibria. There is only one weakly dominant strategy profile, but there may be, if there exists any, but there may be other equilibria and other vectors of max-min. But if you have a vector of strictly dominant strategies, then it's the unique equilibrium, and that's the unique vector of max-min, and the proof is simple. So first of all, for every player, it's the unique best response, so it's the unique equilibrium. Actually, a strict equilibrium, I must say. It's actually strict. Now, in formulas, we also now let us prove that it's the unique max-min. Now, for any strategies of the others, and any other strategy of play I, it's strictly better to play SI than play that other strategy, because that's we assume it's the strictly dominant strategy. Now that's also there for so to minimize over all those, and if when you have SI, the minimum player I cheat over all the possible strategy of that is strictly better. Strictly better than the minimum player I can cheat of all those strategies. When playing any other thing, of course, yes, any other is I prime. Means that SI is the only max min strategy. And the statement I promise you will see that when we have a Nash equilibrium, every player gets in the equilibrium at least what the player gets in a maximum. Now, please notice there may be no, excuse me, the equilibrium does not have to be a maximum. It is not the same. But what you get in an equilibrium is at least as good as what you get in the maximum. That's important. Why? Okay, well, the value of for anything you do, notice that what you get for anything you do, when the others play what they do in an equilibrium, is at least as good as the worst thing you get for the same strategy as I, when the others play the worst, simply by definition of minimum. Now, of course, they assume that minimum exists in all that. For example, it's finite or just minimum. The minimum. Now, the utility of player I in an equilibrium, by the definition of an equilibrium, it's the best response, is the best utility player I can get when the others play what they play in the equilibrium. Now, by substituting what we saw here, we can just substitute this minimum instead of the utility player I can get when the others play what they play in equilibrium, and that's going to be the minimum, and that's going to be the maximum. And we have arrived at what we wanted. Player I gets in equilibrium is at least what player I could get if there exists a maximum, if there exists equilibrium, then that's what we have. Okay, now let us look at what is the influence of eliminating weakly dominating strategy. We know that it may change the set of mismatch equilibrium. It may not add new ones if you don't delete infinite numbers of weakly dominant strategies. What else can we say about that? Now, what can we in particular say about the security notion and eliminating weakly dominated strategy? So, given a game, I think that also from Macher and Zamir, I'm not sure. Yeah, I think that's the theorem from them, but they presented in a bit of a different notion way. There, I think still. I think I can still write from there. For given a game, assume that there is a pure structure of player J as J prime, which is weakly dominated by some other strategy of player J, Tj. Please notice, I require it weakly dominated by a pure strategy, not just weakly dominated, because it's important. Now, let G prime be the result of deleting that S prime, Sj prime. So we just cut S prime, Sj prime from the strategies of J. The rest of the strategies remain the same. We look at the Cartesian product of those strategies, and they call that S prime, the new strategy space. Now the utilities, we just restrict the utility functions to the new strategy space, S prime. Then, as we can expect, the max-min value of player J does not change. So again, if we delete the strategy, the max-min value does not change. And that's also intuitive, because I've deleted the strategy which is weakly dominated. It can be kind of overridden in a way, by another pure strategy. So I won't suffer. My security won't suffer. Now, please pay attention. If it had been dominated, but not weakly dominated, I would not be able then to say that I can securely do something instead of it, because I won't be able to pinpoint a pure strategy, which is always at least as good. So we use the fact that it's weakly dominated by a pure strategy, as then we will see that exactly indeed important. That's actually an example of mine, not or I use the example of Holzman maybe. Anyway, that's an important thing that they I think don't mention in the book, that if that's not weakly dominated by a pure strategy, then the theorem does not necessarily hold. So let us prove the theorem formally, despite that it's of course appealing intuitively. So we assume that Tj weakly dominates as J prime. And therefore, the worst thing that can happen to player J when she claims a J prime is that not better than what happens to her the worst when she plays to J. And of course, what she plays to J is not better than when we just maximize over the worst thing that can happen of all the strategies besides Sj prime, because simply Tj is one of those. Now, therefore, the value of player of the value, the mean max the value of player J, by definition, it's max min. And we look at, we can say that, let's split that. So to max min, or all strategies besides J prime and over Sj prime, and look at the maximum possible. Now, since we know, and we saw this already before, what happens over Sj prime is not better than what happens if we maximize over all the strategies besides Sj prime. So the maximum is at most simply is it's equal to the maximum of all the strategies other than Sj prime, and that's by definition the maximum value after deleting Sj prime. So the maximum value before is exactly the same as maximum value. And as I said, that we've shown that if we delete the strategy of a player, which is weakly dominated by a pure strategy, then the maximum value of the player is intact. But if the domination is not by a pure strategy, then even a strong domination will not be enough. For example, I think why it shouldn't hold, not necessarily intuitively, but now let's why it does not necessarily hold intuitively, but now let's look at an example which completely shows. Here, column R is pure, is strictly dominated. by half column N and half column C. But it's not, but if we delete that column, the max min of player J of player 2 strictly decreases, because when we have column R, what is the worst that player 1 can inflict on player 2? On player 2 plays L, -5, and player 2 plays C, it's -5, and player 2 plays R, it's -4. So it's the maximum or the minimum, it's a maximum over all those numbers, and that's -4. Now, when we delete R, then the worst becomes the maximum over -5 and -5, and that's -5. So despite that R is itself not better than a combination of L and C, by definition of maximum, which does not allow for this probabilistic combination, the max min comes out. Now, deleting weakly dominant touch of player leaves her max min value intact, or a weakly dominated, excuse me. I have made a typo. Deleting a weakly dominated strategy, by your strategy. So deleting that a weakly dominated strategy of play leaves her maximum value intact. If that strategy is weakly dominated, if the strategy is weakly dominated by a pure strategy, as we showed, it's necessary. Now, what about the max min of others? Now, intuitively, now that others have less option to cover again, so that max min can only improve, and that's true. So max min can increase, but it can never decrease. Now, let's see an example and then prove it. So an example is that the max means the mean, so the worst player 1, the role player can impose on player 2, is that when player 2 plays L, it's 0, when player 2 plays R, it's 0. So the max min is 0. Now, if player 1 deletes B, the way B is strictly dominated by T, but it does not matter. It works for any thing you delete, because the logic here is that you just decrease the space of possibilities. So decreasing B makes the worst that player 1 can do for player 2 1, because 0 here is not valid. Now it's 1 and 0, and the maximum then max min is 1. So the max min of player 2 has increased from 0 to 1. It can increase, and yeah, we prove that the deletion of any pure strategy may increase the maximum value of the others, but never decreasing. And let's look at the game. And for any pure strategy, if G prime is the result of deleting the pure strategy, so basically SK prime is the SK minus the strategy, the other strategies remain the same. We just look at a new Cartesian product that is, they call it S prime. And the utilities are simply the restrictions of the original utilities on the S prime. And in that game, the max min of any other player besides K cannot decrease. Please notice that the utilities, by the way, the restriction on all the S prime, not only on the S of the player. Just a reminder, the utilities are functions of all the strategies. It's important what all players do in general. Okay, so let us prove that the theorem, the proposition. It's very simple. So the new strategies of player J are strictly included in the previous ones. Therefore, the minimum of the new strategies can only increase, never decrease. Therefore, excuse me, the new strategy of players other than player J. J is any player which is not K. So players other include K. The new strategies of player other than player J has strictly shrunk. Yes. And therefore the minimum of all those strategies, of what the others do, can only become bigger. Because there is a smaller space on which to look at the minimum. Therefore, the max min of player J is only can only increase, never decrease. Proved. Now, finally, we get with the question: are weakly dominated strategy necessary? Are they indispensable? And if yes, when?